as we are talking about reaction thermodynamics, right? Thermodynamics of reactions in multi-component systems, and we are looking at multiple reactions. So when we looked at multiple reactions, again we did the conservation of elements, we had also disequilibrium constants, and as a result we had several equations, and we can solve them numerically. Now this equation basically is called the law of mass action, right? And delta nu basically is R plus S minus L plus M for this reaction, where L moles of L react with M moles of M, right? So basically L moles of L react with M moles of L to produce M moles of M to produce R moles of R, which is one product, and another. So these are the products, right? R and S are the products. So this is a product, this is another product, and these are the reactants. L and M react, right? And if you see, this is R plus S, and this is minus L minus M, and that is the delta nu, or sum over the all nu. So basically, if you do the sum, so this is the sum or nu, or this is the change in there. So delta nu, or the way we have initially introduced it, it is basically the sum nu I, right? Sum nu I is the same as delta nu is nothing but sum nu I. Sum nu I. So basically, if I look at delta nu is nothing but sum of I equal to 1 to whatever be the number of species, 1 to say C, and this is basically nu I, right? So basically, and as I told, for products it's plus, and for reactants minus. So basically, this basically becomes, if you look at this reaction, it is R plus S minus L minus, right? The same thing that we have drawn, right? So basically, and also we know this, right, that A equals to minus RTL and KP plus RTL and RT delta L and PI, and that is nothing but RTL and QP, and you have this relation. So, and you have also the Helmholtz equation, from which you can write this, like the del L means how the equilibrium constant changes as a function of temperature, and it is related basically to the delta H0, the delta H0 or delta HT0, whichever you call it, okay, and that is the delta H0 of the reaction, right? And delta H0 can be endothermic or exothermic, right? Reactions can be endothermic or exothermic. That is something that we have explained. Now, if you have all gases, so many times what we do is we basically can also use ideal gas law, like PIV equals to NIRT, or PI equals to NI by V RT. So this becomes RT. So NI by V is nothing but the concentration, right? So CR to the power R, CS to the power S. This is basically, CR is basically concentration of R in moles per unit volume, right? You can also have, so this is where I was basically pointing to. You can also have heterogeneous reaction, and one of the heterogeneous reactions is like oxidation, where you have a metal which is solid, which combines with oxygen which is gaseous, and forms a metal oxide which is again a solid. So here also calcium cyanide, right? So CN2. So CN2. So this is calcium carbonitride. You can tell carbonitride because this is calcium CN2, right? So carbonitride. So if you look at that, so this is basically a solid. This is basically a solid. Now it reacts with water vapor, which is gaseous, forming calcium carbonate and ammonia, right? It produces ammonia. So basically it's giving you, again, so it is giving you one solid again here, reacts with gas to form a solid and a gas. Now for gas, you will write mu I equals to mu I0 plus RTL and PI, where PI is the partial pressure of component I in the gaseous state, right? GI0 plus mu I0 is nothing but GI0, and RTL and PI is basically, PI is the partial pressure of I in the gaseous state, right? But for solid or liquid, you have mu I, which is nothing but mu I0 or GI0, right? There is, this term is no longer present, right? Now if you have that, then A, that is affinity. So again, this is affinity. Affinity is nothing but some sort of a, is basically delta G. We can write this as delta G. Sorry. So is equal to delta G0 plus RTLN. Now if you see, RTLN Pi is only for 3H2O as well as for 2NH3, right? So basically RTLN Pi or RTLN PH2, right? RTLN PH2, and then RTLN PNH3 is also there, right? And you are looking at that. Now you have the product, right? Product has this coefficient of 2. So basically, if you look at this, this becomes mu 0 plus RTLN PNH3. However, you remember that, and this is basically on the product side, and on the reactant side is mu 0 plus RTLN PH2O. However, if you remember, A is nothing but some nu I, right? So nu I means basically you have now, in this case you have minus 3. So this becomes, now this becomes minus 3 mu 0 minus 3 RTLN PH2O, right? Partial pressure of water vapor, and you have plus, right, because it's the product side, 2 mu 0 for NH3. So this is mu 0 water and this is mu 0 NH3 minus plus 2 RTLN PNH3. So that's why you get in the numerator PNH3 squared, and the denominator you get PH2 cubed, and you have delta G0. Now delta G0 is basically 2 G0 of NH3 plus G0 CaCl3 minus 3 G0 H2O minus G0 CaCN2, right? So this is what it is, because you not only have this term, or you not only have these two terms, you also have, so for mu 0, the standard chemical potentials or the standard free energies, you have these states, right? Every product comes. Now only thing, the solid products, you have only mu 0 I, which is nothing but Gi0, right? So basically you have G0 of NH3, you have G0 of CaCl3. Now these are the products, right? So basically if you look at the stoichiometry, this is plus 2, this is plus 1, right? This is plus 1, this is plus 2, and this is minus 3, and this is minus 1, right? That's the idea. So, but Kp, that is the equilibrium constant, is related to the partial pressure of the gaseous reactants and products, right? This is the gaseous product and this is the gaseous reactant, right? So that's the idea, right? So basically you have this, right? Delta G0 again is basically summation nu I Gi0 T, and as a function of T and P0, right? Now if you have that, basically Gi0 or delta G0 can be written as delta H0 minus T delta S0, right? This is the definition. G equals to H minus Ts, or delta G equals to delta H minus T delta S. Now you are keeping, say for example, P0 fixed, okay? So P0 you are keeping as fixed. Now you are telling that delta HH0 is nothing but delta H formation, right? Because delta HH0 is for each species. Now you are thinking of the formation enthalpy of each product, okay? Formation enthalpy of each product. So basically you have the formation enthalpy of each product, and you are basically delta H0 basically is then the sum from j equal to 1 to n is the number of species or constituents, and you have again nu j is the stoichiometric coefficient, and that is positive for products and negative for reactants, multiplied by delta HFI0 for each component, right? For each component. So as a result, however, remember the delta G formation for the component, or delta H formation of component, when the component is a pure element, or the species is a pure element, is 0. Right? And also you know that you can basically, you know the Helmholtz, gives Helmholtz equation, but you also know the other relation, right? dH equals to CPdt. So for each component I can write dH equals CPdt. So basically I can do the reaction at different temperatures, and we can calculate say for example nu, so for example, if I am calculating nu I, right, this one, this guy. So if I am calculating this at different temperatures, if I want to do it at different temperatures, so at those, how do I add this temperature effect? Because each component has a heat capacity, and heat capacity itself can be a function of temperature. So you have Cp dt, right? Remember, Cp can itself be a function of. Okay, so basically, as you can see here, that this is that. So now, if I basically want to see how the equilibrium constant changes with temperature at a fixed pressure P naught. Okay, by the way, I have used a P naught. There are various ways, but just to be consistent, for a given pressure or something, I am using the superscript P naught. So here also I am using superscript. Does not really matter, just to be uniform in complete. P naught is the total pressure. P naught is the total pressure. Now P naught is fixed. P naught is fixed, and you are looking at del LNK del T. Again, you are basically looking at the Gibbs-Helmholtz equation. So which gives you delta H0 by RT square. But why delta H0? Where is the minus sign gone? The minus sign is gone is because LNK itself is minus delta G0 by RT. Minus, right? It is minus delta G0 by RT. So if you have this, you have so since LNK is minus, so basically you get, say, minus delta H by T square, right? So basically minus becomes plus. So this, right, if you look at the Gibbs-Helmholtz equation, yeah, see, there is a minus H by T square, right? There is a minus H by T square. So basically now you are looking at the correction, and once you have done the correction, you basically get this delta H0 by RT square, right? So del LNK del 1 by T, because you have del LNK del T, and this becomes R1 by RT square. Now if I take T square here, so if I take T square on this side, so basically del 1 by T is minus nothing but minus 1 by T squared, and there is a minus sign, right? So minus sign, I'm putting it again here, I'm putting it here. So but there is a 1 by T squared. So 1 by T square is there, and as you can see, it has this 1 by T square, and as a result, this entire thing is nothing but minus delta H0 by R. Now if you look at that, if it is, okay, del LNK del 1 by T at constant pressure P naught is equal to minus delta H0 by R. Now if you see that, if I plot LNK versus 1 by T, so 1 by T is increasing this way, that means T is increasing the other way. Because if T increases, 1 by T decreases, right? So if you now look at this, so T is decreasing towards the origin, right? T is decreasing towards the origin, and 1 by T is increasing away from the origin, right? If 1 by T increases, 1 by T increasing means, so if you look at this, so it is basically, now this is where again the fallacy should not come. So if you look at the principle, if T increases this way, if actually 1 by T has to be plotted here. So as temperature increases, 1 by T decreases, correct? So as temperature increases, 1 by T decreases. So as a result, T itself is increasing towards the left, and 1 by T is increasing towards the right. As temperature increases, as temperature increases, 1 by T decreases, right? So if 1 by T is increasing this way, then the temperature is decreasing this way, right? Temperature is decreasing towards the right, right? Temperature is increasing towards the left, right? Now if that is so, if you plot this, you get LNK, because if you see there is a minus sign. Why I am doing all this? Because there is a minus sign here. If I plot del LNK del 1 by T at constant pressure, which is equal to minus delta H naught by R. Now if you look at that, you have LNK versus 1 by T. Now if you look at that, you have the slope here. In one case the slope is positive when delta H naught is negative. When the delta H naught is negative, then you have that means you have exothermic, right? This is basically exothermic reaction. And this is endothermic, right? Where there is absorption. So endothermic follows the other way. If you look at del N K versus 1 by T, then basically endothermic goes this way, while exothermic goes the other. Now there is a very important principle which I think many of you know, which is called La Chatelier principle, which tells that a systematic equilibrium when subject to a perturbation responds in a manner that nullifies or eliminates the effect of perturbation. Nullifies or eliminates the effect of perturbation. Okay, so basically if you look at endothermic reaction, think of an endothermic reaction taking place, ln k increases as a function of 1 by t, right? As 1 by t increases, ln k also increases, and del ln k del 1 by t is basically positive, right, for an endothermic reaction. Now if you see that, so if I perturb the system by increasing the temperature, then what happens? Reaction, now if I have increased the temperature, I am basically endothermic reaction means it absorbs heat for the reaction to occur, right? For the reactants to react and form products, you require to supply heat to the reaction. Now if you see that if I just increase the temperature of the system, then what happens? The reaction shifts towards the reactants because it has higher enthalpy than the products, right? So if I have endothermic reaction, then the reactants will have higher enthalpy, right? Because the reactants you are supplying heat, right? And then products form. So you are supplying heat, the products, the reactants are absorbing the heat, and then only products are forming. So if the reactants have had enthalpy than products, now if I increase the temperature, the effect is such that reaction will shift towards the reactants. Why? Because heat provided to increase the temperature goes into the reaction, thereby cooling the system and reduction of heat. Right? If I am increasing the temperature of the system, so then you are basically going back to the reaction is shifting towards the reactants, because if it shifts towards the reactants, then the heat provided to increase the temperature will go into the reaction, right? Because it requires to absorb heat to complete the reaction, right? So as a result, the reactants, since the reactants have higher enthalpy, then we have to so basically heat provided to increase the temperature goes into the reaction. Now if it goes into the reaction, that means like the reaction is absorbing more heat, or reaction is absorbing heat, thereby cooling the system. So if I increase the temperature, I am supplying heat to the system. The way the system will behave as to nullify this effect, that is, as to reduce the temperature of the system. How does it do that? By basically shifting towards the reactants, because reactants will require to absorb it to form products. So if the reactants have absorbed this excess heat, basically the system remains cool and the temperature decreases. Right? This is something that you have to understand. So basically, the way the system will behave as to nullify the effect. So if you have imposed some effect on it, so basically this is very important, that when such perturbation responds to a manner that tends to eliminate the effect of perturbation. Basically, you have increased the temperature. As a result, you want to see for an endothermic reaction, what is basically delta H is negative. Delta H is negative means products minus reactants is negative. Then products has less enthalpy. So basically, if products have less enthalpy, it is than the reactants. That temperature of the system, if I have to increase the temperature, I am supplying more heat. Now this heat basically can go to the reactants, and this heat can be utilized to the reactants, because the reactants will absorb this heat and then they will form products. And as a result, the system will cool down and it will nullify the effect of increasing temperature. Right? That's the idea. So this is for the endothermic reaction. For exothermic, it's very similar. Say, for example, if it's an exothermic reaction, the products have higher enthalpy than the reactants, and as a result, if I increase the temperature, since the products are higher enthalpy, it wants to release the heat. So basically, you move towards the product. So basically, you will have a movement towards the reaction will move towards the product, right? So it will shift towards the product. So more product will be evolved because product has more enthalpy. So that ultimately, if the product has more enthalpy, so it is basically rejecting the heat, right, out to the surrounding, as a result, decreasing the temperature. So if I increase the temperature, the reaction will proceed in such a way as to decrease the temperature of the system or cool the system. That's the idea. Now, if you think of P, now you are telling this is basically the dependence of K on temperature. That depends on the equilibrium constant of temperature. Now, what about the dependence of equilibrium constant of pressure? Now, if you do that, you have, if P is P naught, say for example P is chosen to be the 1 bar or the upper pressure of component I, so it can be chosen to be 1 bar, which is basically the atmospheric pressure or the pressure of component I. You can also choose the pressure of component I as that standard pressure. Then basically the delta G naught does not vary with P. However, if we take the system pressure to the pressure, then there is a variation. Why? Because see, you have delta G naught basically is again given by nu I Gi naught T, right? This is for the system. Now del, so basically this is a relation, right? Delta G naught Tp is I equal to 1 to n, that is for all components, it is Gi 0 T. Now if you look at that, delta G del P at fixed temperature is basically nu I and then delta Gi 0 del P, right, at a fixed temperature. Now basically del G del P is nothing but V, right? Del G del P is nothing but V. So I have to write the V properly. Right? Vi0 is basically the volume of the species I, volume of species I in the standard state, right? In the standard state, that is the pure state, that is only that species exists, okay? And nu I is the stoichiometric coefficient, right? Now, if you look at that, you see del G, this is del G naught del P. Now del and G naught has a nu I, right? G naught has a nu I, right? So del G naught del P is basically summation of nu I Vi naught T. Now if I have that, del G del P is that, so you have del G del P, right? And you are looking at del NK del P, right? Del NK del P, which is basically, if you look at that, the del NK del P is nothing but minus 1 by RT del delta Z0 by del P, right? Del delta Z0 del P. Now del delta 00 del P basically is the 1. Now if you have that, if you do this combination, then basically you eliminate the nu I, right? You eliminate the nu I and you get the overall, the equilibrium constant, the change in pressure with change in pressure is equal to minus delta V naught by RT. Now if you see, if delta V naught is less when their products are formed, then as pressure increases, the K also increases, right? Because as products are forming, the volume is basically, delta V naught is basically negative. That means volume of products is that of than that of reactants. So as a result, as pressure increases, K will also increase in the case where delta V naught is less than 0. However, when delta V naught is greater than 0, then if delta V naught is greater than 0, delta V naught is basically V products minus V naught products minus V naught reactants. So basically, right, with V naught, because nu I Vi, so delta V naught, as I showed you, is equals to summation I equal to 1 to n, right? Summation I equal to 1 to n, and this is nu I Vi, right? Nu I Vi. So basically nu I Vi naught means positive for products. So it is difference between products and reactants, right? If delta V naught is greater than 0, that means the product is having more volume. Now if product is having more volume, if pressure is increasing, then you want to reduce the equilibrium constant, so that you know the effect of increasing pressure is nullified, right? If delta V naught is positive, you basically, if you increase the pressure, the equilibrium constant actually comes down, right? Because reactants are filled, right? Because it has more volume, right? The products have more volume when delta V naught is greater than 0. When delta V naught is less than 0, products are filled. Okay, so if you look at the temperature dependence and pressure dependence, you understand very carefully the Last-Chatelier principle. Now there is also another Last-Chatelier principle which becomes very useful when you look at this charts and charts for oxidation of metals, right? Again, I will look at the reaction with pure oxygen, but you can also look at the CO2 ratio or H2H2 ratio, right? And I am looking at a reaction like A plus B, A combines with B to form C, right? And you have basically delta G is Gc minus Ga minus G, So again, it is equal to, say, it is equal to 0 at equilibrium. Now delta G naught is basically minus RTL and Kp. That's what we have seen. And Kp is Pc by Pa times Pb, where Pc is the partial pressure of C, and Pa and Pb are partial pressures of A and B. Now, if you have a heterogeneous reaction where metal is a solid, right? In this case, the metal is a solid. It reacts with a gas and forms a solid. Now, if it reacts with a gas and forms a solid, first thing that you notice is that if it is reacting with a gas, it is consuming the gas. Gas has much higher entropy, right? Much higher entropy than the solid, right? As a result, the gas is the sole contributor to entropy, and as a result, as the oxygen gets consumed or the gas phase gets consumed, when it is oxidizing, so what happens? This reaction basically inherently is a reaction in which you have negative enthalpy, right? Within the system, there is a negative enthalpy in the system. Now, right, as long as the metal is solid, right? So metals and oxides are simply pure solids, that is, they are in the standard state and their activity is 1, right? So basically, if that is so, if I look at the equilibrium constant, Kp equals to, it is just nothing but, because you have only oxygen partial pressure, so it is nothing but 1 by P, right? 1 by PO2, which is equal to Kp. Now, if you look at that, what is the PO2 at equilibrium? Okay, at a given temperature. What is the PO2 at equilibrium at a given temperature? Now, if you look at this, you have delta G naught, which is RTL and PO2, and delta G naught at 0K, there is no entropy change. So, delta G naught at 0K basically becomes delta H naught, and delta G naught del T is minus delta S. Now, delta S naught is negative, right? Since there is an elimination of oxygen gas during oxidation. Now, if delta S naught is negative and delta G naught del T is minus delta S naught, it is always positive, right? This slope delta G naught del T is always positive for any chemical reaction. So, this is from Dwight-Palms Cambridge. I have, so which has CC means a Pretty Commons license. I have taken this Ellingham chart. In this Ellingham chart, you have different oxides, right? Different metals and the oxide formation. If you look at that, the slope is positive. As we saw, delta G naught del T is minus delta G naught del T is minus delta S naught. Now, if it is minus delta S naught, you will wonder why the slope is then positive. This is because delta S naught itself is negative. Why it is negative? Because you are consuming all the oxygen, right? So delta S naught itself is negative. So minus of delta S naught will basically give you a positive slope. Minus of delta S naught will give you a positive slope. Now you have this positive slope, but in order of reactivity, these oxides have been arranged. For example, iron oxide, okay, it goes to quite high, right, above 1000 degrees. Iron oxide basically is very stable, right? And then you have nickel oxide. So is it very stable? So if you have increasing, so basically if you see, this is the standard free energy of formation of oxides. Now the standard free energy of formation of oxides, basically if you look at that, so what do you have to suggest? Say for example, which will be more stable, alumina or nickel oxide? Okay, so basically if you look at alumina, it has a much lower standard free energy value, right? Or much higher standard free energy value. But this is, remember, this is negative value because delta G naught is minus RTL and P naught, right? Minus RTL and P naught, right? Because you have 1 by PO2, right? 1 by PO2. If you look at that, Kp is 1 by PO2. So it is basically minus RTL and P. So delta G naught is minus RTL and P naught. If you can look at that, that is exactly what is negative. Now, if that is so, inherently if it is negative, then basically delta G naught is basically becoming minus RTL and Kp. Minus RTL and Kp is 1 by PO2. So delta G naught equals to RTL and PO2, right? So it is RTL and PO2. And if you can see here, the more negative the energy, the more negative the standard free energy, the more stable the oxide. The more stable the oxide. Now there is one interesting point that I want to tell, that at constant temperature, for example, G equals G naught plus RTL and P by P naught. This is correct, right? This we have no argument about this, right? But put P naught equal to 1 atmosphere. Then basically you get delta G equals to RTL and P. Right? So basically, if you put so delta G is RTL and P. Now, if you look at that, so put P naught equal to 1 atmosphere, right? So you are putting P naught equal to 1 atmosphere, and if you are putting P naught equal to 1 atmosphere, then basically RTL and P minus RTL and P naught, and RTL and P naught is basically 0, and you have RTL and P here, and you have delta G, right? So that's the idea. Now, if you look at this, that the delta G, that is G minus G naught, right? Delta G is RTL and P, right? Delta G naught is RTL and PO2 or RTL and P, right? Now, how do I know what is the oxygen partial pressure for a given reaction? Say, for example, if you look at that, you have this scale, nomographic scale of oxygen partial pressure. Now, if you look at this conversion, say for example, you are looking at the conversion of nickel to nickel oxide or cobalt to cobalt oxide or so on, or silver to silver oxide. And so basically what you are doing is, from the origin, you are starting to draw a line for the desired, for the desired temperature. You are starting to draw a line here, and this point cuts here. And then what you basically do is that if you extend this point, you hit the nomographic scale, and you are getting something like 10 to the power minus 18, right? 10 to the power minus 18 is what you get, right? This is log partial pressure. So since it's log partial pressure, what I am telling is the partial pressure is like 10 to the minus 18, and this is basically at certain temperature, at a lower temperature, right? It is certainly at a much lower temperature. This is at a lower temperature. Now, if you look at the curve Ag to Ag2 silver oxide, again it has a positive slope. Why? Because delta S naught is negative, minus delta S naught is del G. Basically, so if it is, you are looking at del G del T, right? It's a function of, so x-axis is temperature, right, and y-axis is minus of. So you have temperature, and here you have delta G. Now, if that is so, now if you look at a high temperature reaction, say for example a reaction that is occurring here. Now, if you look at this, you will have an oxygen partial pressure value which is much higher. Now, this is actually not that great, because the higher the temperature, the oxygen partial pressure value is much larger, right? At higher temperatures, right? This is at some temperature of 1500 or 1400. So the point that I am trying to say here is that at higher temperature, why is it that at higher temperature you have less, you have more oxygen partial pressure required? At higher temperature, as you are oxidizing, you are consuming oxygen. Now, if you are consuming oxygen, if your partial pressure becomes less at any temperature, so as you are consuming oxygen, your oxygen partial pressure is reducing. Now, if your oxygen partial pressure, for example, at higher temperature falls below, say in this case like 10 to the power minus 9, if it falls below that, then basically the reverse reaction becomes possible. That is, silver oxide decomposes or dissociates into silver and oxygen, right? So basically, as you go to higher temperatures, the partial pressure requirement increases, right? It is like 10 to the power minus 9, if you can see here. So it is like 10 to the power minus 9. So the blue line, if you see that what I have drawn here, right? It becomes 10 to the power minus 9, right? But see, at much lower temperatures like here, you basically had 10 to the minus 18. Now, the problem is 10 to the minus 9 atmospheres is that if you are above it, then there is no problem, right? Oxide is stable. However, if you fall below it, and that is what exactly will happen as your reaction proceeds. As your reaction proceeds, that is exactly what will happen, right? So basically, equilibrium partial pressure is a pressure at which the driving force for oxidation drops to 0. There is no driving force for oxidation anymore, right? You basically are getting Now, if PO2 is greater than PO2 equilibrium, then delta G oscillation is less than 0. So, the reaction will proceed forward. Correct? But if PO2 becomes less than PO2 equilibrium, becomes less, right? If it is greater, then there is no problem, right? You have 10 to the power minus 9 as the threshold value. If you are always greater than 10 to the minus 9, if your oxygen partial pressure is greater than 10 to the minus 9, then there is no problem. There is no problem of destabilization. However, if the oxygen partial pressure falls below the PO2 equilibrium, that is read from the nomographic scale, then what happens is the reverse reaction becomes possible. That is, instead of going from silver, so if instead of going from silver to silver oxide, I can go from silver oxide to silver, or alumina to aluminium, right? So basically, we have to be very, very careful here that the partial pressure of oxygen greater than partial pressure of oxygen at equilibrium, then there is no problem, the oscillation proceeds. But on the other hand, if PO2 is less than PO2, if it is less than PO2, that means it falls below, and this is a particular problem at a higher temperature. At higher temperature, for example, PO2 may be less than PO2 equilibrium. In such a case, instead of going from M plus O to, so if I want to balance, say, goes to say M. Now, if you see, right, this is the reaction. Now, if you see, as this reaction is happening at high temperature, your partial pressure, as it is happening, the driving force has to go to 0. So basically, as the driving force goes to 0, basically you have the partial pressure at which the driving force goes to 0, and then what happens? Your partial pressure starts falling down, and if it starts falling below the threshold pressure, the threshold partial pressure at that given temperature, right? At a given temperature, particularly at high temperatures, then what starts happening? The reverse reaction starts happening. The forward reaction stops, right? So this is the idea of so basically 2M plus O2 is 2MO. So this is the reaction. Now, if you see, delta G is less than 0 if PO2 is basically greater than P equilibrium. However, it is equal to 0 if PO2 equals to PO2, and it is greater than 0 if PO2 is less than PO2. Now, if partial pressure of oxygen is less than PO2 equilibrium, then the delta G of the reaction, of the forward reaction, becomes positive. As a result, the forward reaction does not ceases, and you get a reverse reaction. Yes, that is the MO basically is now dissociating into metal and oxygen. Now, I will very quickly describe interfacial phenomena. Interfacial phenomena I have not described so far. So, all our phase diagrams assume that you have alpha phase, beta phase, or all these phases, but these phases share a boundary, and that boundary is, the phases are infinite in extent, and they share a boundary which is completely flat. However, in real systems, you have particles, and the particles have curvature, right? The particles, like if you have a spherical particle, then there is a curvature with it, right? Because there is a radius of curvature, and inverse of radius of curvature is what is called curvature, right? But if you look at a straight line, say for example you have a huge alpha phase, say for example you have this alpha phase, and then you have say beta phase. So basically, if I draw this correctly, you have to think of sub volumes, right, in the composite system. If you think of sub volumes in a composite system, say for example in the sub volume, then this is a flat interface. Flat interface means if you have a completely flat interface, then basically the radius of curvature is infinity, or curvature is 1 by infinity, which is 0, right? And you remember there are two terms here, H, which is mean curvature. So if you look at this plane, right, this is like a dividing surface between alpha and beta. Think of this. This is like you have alpha here, you have beta here, and then in this plane, basically you have a plane normal. That's the surface has a surface normal, and as you can see, that there are two radii, right, in this surface. There are two radii. One is R2. To define the surface, you require two radii. One is R2, another is R. In such a case, you have two curvatures, right? One is 1 by R1, another is 1 by R2. For spherical particles, if you have a completely spherical surface, then basically 1 by R1 equals to 1 by R2. So it becomes like half into 2 by R, and that is basically nothing but 1 by R when you are basically looking at a sphere. However, it is not always sphere, right? So as a result, we need to understand, okay, this definition. So one of these definitions is called mean curvature. So this is the mean curvature. Right? And this mean curvature is going to basically, this mean curvature particularly for non-flat surfaces, that is spherical surfaces or cylindrical surfaces or something like that, it has a big effect, right, on different phase transformations that take place, right? It also has a big effect on the solubility, right? So this is something that I want to tell you. And remember, Gibbs is the one who basically looked at the surface excess and wanted to understand the surface excess. Later, Kahn and Hilliard and all these guys have improved it a lot, but initially it was Gibbs. And Gibbs thought of a physical surface of discontinuity between alpha phase and beta phase, and he named it as sigma phase. Now, in that physical surface of discontinuity, if you have some property, so if you have an extensive property and if you have a per volume intensive property, limit v tends to 0, b by v. So B is an extensive property, but BV is an intensive property. Then basically, if you look at the profile of BV as a function of distance, what do you see? You have this intermediate region, which is basically your dividing surface, right? This is basically it's not really a dividing surface. It's like a transition zone between one bulk to the other bulk, like alpha to beta is a bulk. And then there is a physical surface of discontinuity. Now, this physical surface of discontinuity, I have exaggerated it when I drew. But if you look at that, the variation of the small bv, so this is small bv, the way it varies. So, most likely it varies like this. Most likely it varies this way. Right? If that is so, right? This S-shaped curve, right? So, basically you have this S-shaped curve, and if you see that S-shaped curve, the middle region basically is indicating the physical surface of discontinuity. Now, if you look at that, Gibbs came up with a sharp interface model, and he told that there is a sharp, so in this transition region, physical surface of discontinuity, he constructed a dividing surface. He constructed a dividing surface. He called it Gibbs dividing surface, and on this surface, he is basically looking at the excess properties, right? Excess properties basically system with interface minus bulk. So I have alpha phase, beta phase, and I have this alpha beta. They are basically the total system. So you have alpha phase, you have beta phase, and you have alpha beta interface. And on the other hand, in bulk, you have alpha phase separately, beta phase separately. Now B system minus B bulk basically gives you this B system, which gives you B excess, right? The excess associated with the extensive property B. So excess associated with, say, or you can think of like interface energy excess or free energy excess or whatever it is. Now the point is, if you have the free energy excess and if you know the cross-sectional area, basically, so for a bulk, you have a material property, an extensive property, and if you tell entropy is like the extensive property, and if I want to express entropy per unit volume, then basically I have to divide by volume. However, if it's a surface property, I have to only divide by area, right? The excess property has to be divided by area only, and Gibbs dividing surface is nothing but a two-dimensional area that separates two three-dimensional volumes. One is the alpha, bulk alpha, another is bulk beta, right? Now, if I continue this, so basically if I continue this, what I have essentially is an extra term, SSDA. Now, if I go on doing this, I have this extra term. So, if you see, this is DSCs. Again, I am looking at the same equilibrium approach. I am looking at expanding it, and you have this additional term, SSD. Now, again, if you look at the isolation constants, you have duc is equal to 0, dvc is equal to 0, and vs is basically the excess volume to the surface, which is again 0, right? Excess volume to the surface is 0. And dnk, then it's for each element of the system, dnk is equal to 0. Now, if you have that and you continue doing this, so basically from the isolation constraint, you can do what? You can write dV alpha in terms of dV beta and Vs. You can write du alpha in terms of du beta and Vs. So, and Us. So, exactly that's what I am going to do here. So, if you do a little bit of manipulation, so basically you have 1 by T beta, and here it was du beta. Instead of du beta, I have written du alpha, and you have also Us, that is the U surface, times T. Right, again you have here, say for example, NKS times T. Now, all these terms which are basically surface dependent have come up, and also you have the excess entropy associated with the surface. Right, this term you should not forget. Now, if you have that, you can rearrange to get the different equilibrium conditions. So, for example, the SCs now gives you this. So, this is the equilibrium condition that you get. T alpha equals T beta, and then 1 by T alpha minus 1 by T beta into du alpha plus P alpha by T alpha minus P beta by T beta dV alpha, because I am substituting. And here also mu alpha minus mu beta. So, basically, if you look at that and you have this T and K alpha, so this is the chemical equilibrium, this is the pressure equilibrium, mechanical equilibrium, this is the temperature, thermal equilibrium. Right? Now, if you have that, think of dA. So, dA, how is the relation between dA and dV? That is surface and volume. So, dA is related to dV by, so I am not giving the full derivation, dA is related to dV by this mean curvature, which is h. So, dA equals to Th times dV alpha. Okay? Or, right, you are looking at alpha phase. Then, 2h dV alpha, and you have also, so what is dV alpha? Basically, it is same as minus 2h dV beta, correct? Now, you have all these terms, so you have the thermal equilibrium, you have thermal equilibrium, you have mechanical equilibrium, you have also chemical equilibrium. However, there is this term SS minus 1 by, so you basically have this term SS minus 1 by T beta US plus K equal to 1 to C U K beta by T beta, right? I should not read the equation, but if you can see here, it is S minus U by T plus mu by T, okay? And mu by T is summed over all components, right? All components. Now, so if you have that, and also you have this chemical equilibrium, right? This we should not forget. Now, if you have that, you basically see the pressures are equal, temperatures equal, but you have this term, extra term, which is SS minus 1 by T beta, right? We are using T beta here for normalizing. So, T beta also we have found, right? We found T beta. Yeah, so T beta is basically one temperature in the beta phase. So, basically P beta by T beta is nothing but temperature. And you're going to have a look at this, and if you rearrange all of these, so basically you have a term, so basically 1 by T alpha equals 1 by T half. So we have a term here, right? This is 1 by T beta and this is US, right? This is the excess term. Now if you look at that, mu K alpha equals to mu K beta equal to 0, or mu K alpha equals to mu beta, then P alpha equals to P beta. However, you have the term in the brackets, which is this term in the brackets, this term in the brackets. Now, if you look at this term in the brackets, and do a little bit of rearrangement, right? If you do a little bit of rearrangement, that means US minus TS minus sigma UK and K. So, basically, if you cos T alpha equals to T beta, right? P alpha equals to T beta equal to T. Now, if gamma, if I can write this, so T alpha equals to T beta equal to T. So, P alpha equals to P beta, and so you have now minus of gamma by T, right? Gamma by T. So gamma I am defining as US minus TS minus US minus TS, U minus TS, US minus TSS minus mu NKS, right? NKS is basically the interfacial concentration. Now, if you see this, all these terms, this energy, entropy, and mole number contribute the interfacial energy, right? So, basically, you have P alpha minus P beta equals to 2 gamma H, and this is like a capillary relation, right? P delta P equals to 2 gamma H. So if you go on doing all these derivations, you at one point you will find that, say for example, in a unary two-phase system, T beta is T alpha, but P beta is P alpha plus 2 gamma, and mu beta again equals to mu alpha. Now if you plug in all of these, you can show that for a curved interface, the capillarity effect will be different, the capillary length will be different. Okay, and basically you can writing delta V in terms of RT by P. Then you have the other process of melting, right? Where so here what is happening? Your pressure has increased, right? Because of the curvature. P beta equals to P alpha. Again, this is positive curvature. If your curvature would have been negative, then it would have decreased. So basically for the two-phase system, unary two-phase system. On the other hand, if you look at melting, you basically see that I'll directly go to the main result. The main result is T curvature. So basically this is TH. Okay, let's call H. H means basically the mean curvature. So TH equals T naught minus 2 gamma Vs by delta S into H. So basically, so you have this entropy change and 2 gamma Vs by delta S. Yes, this is correct. Right, T naught minus 2 gamma Vs by delta S into H, because this is coming from here. Right, if you look at that, this is the equation that you get. Right, how do you get this equation? You have delta S dt, like S dt, and you have 2 gamma V beta dh, which is equal to 0. Right, so S dt minus V dp is what I am trying to look at. So basically you have yeah, so if you look at that, here you have minus delta V dp, so you can basically prove, right, because this is delta S dt minus V delta V dp plus 2 gamma V beta dh. Now if you look at that, you have delta V dp and you have 2 gamma this thing, right, and you are basically taking delta dt equal to 0, so you get basically delta V again you can take as RT by P. So basically you get a different type of an equilibrium, right, because of the pressure, right, because of the curvature, right. Right, there is a change, right. Again, in melting, the melting point, say for example, the melting point of the curved solid, okay, which has a positive curvature, is going to decrease, right, is going to decrease than the melting point that was there when originally the liquid solid surface was flat, right. It is going to decrease. And here you can do a little bit of manipulation. Now if you look at that, you have 2 gamma and Vs is what? Vs is the excess quantity associated with the volume, correct? Associated with the volume. So beta is the solid, alpha is the liquid, and you have delta S dt and 2 gamma V beta, right? V beta is the volume of the beta phase. So if you look at this, minus 2 gamma V beta by delta S. So basically TH is here, you should not use S. Basically this is basically the beta phase, right? Minus 2 gamma V beta by delta S. Delta is the change in entropy. Now that is basically TH basically reduces, is what I am trying to say. You again go through it. I am not going through it I am going through it pretty fast. Okay, if you go through it slowly, then you will understand what I am trying to say. Say for example, if you have understood this particular, that's capillarity, right? You have understood capillarity, you see that there is an extra pressure, right? So basically P beta is now not equal to P alpha, but it is equal to P alpha plus 2 gamma H, where H is the mean curvature, right? And gamma is the interfacial energy. Now if you look at melting, again have a look at melting. So before that, what I have established, we have established some very simple ground rules. That is, for a unary two-phase system, how does the equilibrium change? T beta has to be equal to T alpha. P beta is P alpha plus 2 gamma H, where H is the mean curvature. Mu beta equals to mu alpha, right? And you have this term, these equations, right? These equations are already there. You know these equations, this one and this one. Now you are basically looking at d mu beta, and you have S beta dt, because T beta equals T alpha equals T. And then you have V beta, and then you have dP alpha plus 2 gamma dh. Why? This basically is because dP beta is dP beta. So it's because of this relation. So dP beta equals to dP gamma plus 2 gamma dh. You can also have 2 HD gamma, but the point is that we do not currently we are not using it, because if you have an excess quantity like A gamma, here is the area, and this is interfacial energy per unit area. So if I do D of A gamma, you have actually two terms. One is called A D gamma, right? And you have gamma D. In general, we look at the gamma dA part, we do not look at the eddy gamma part, that in general. But however, if you have the eddy gamma, basically, what does it mean? It basically means that there is a differential with respect to the interfacial energy, okay? And this is basically some sort of a interfacial. If you think of this interfacial energy, it's like a force, right? It's joules per meter square, or it is like Newton per meter cube. So if you think of this, this is a, it has this, it's like a torque term, right? So I do not want to go deep into the torque term right now. I do not want to go to the AD gamma contribution, but what I am telling is dA gamma for us now is nothing but gamma times dA. But there is a change in A, right? So that's that. Now if I am looking at that, so basically I get this delta V, which is V gas minus V liquid. But V gas minus V liquid is very small compared to V gas. So basically delta V is nothing but V gas. So V gas is nothing but RT by P, right? V gas is nothing but RT by P. Now you are looking at melting temperature. Now if you use the same argument, you basically see delta S dt plus 2 gamma V beta dH, which is equal to 0, right? 2 gamma V beta dH is the extra term that you have. And you have dt equals to minus 2 gamma V beta by delta S dH. And you are doing an integration. So basically what you see, as the particle becomes spherical or smaller with a radius of curvature, which is non-zero curvature, with non-zero curvature, you basically see a reduction in the melting. Now, if you have a spherical particle that is immersed in an air-rich matrix, this is also an interesting phenomenon. What you basically can see is that the liquid particle containing, so basically this equation, the equation that we derive is called, this equation is basically called Kelvin's equation, and the Kelvin's equation, the crux of the equation is this. So delta G is 4 third pi r cube by VL, and GL minus GV, that is the free energy of the liquid phase minus the free energy of the vapor phase, and you have 4 pi square gamma. 4 pi r square gamma is basically for a spherical particle, right? You are taking a spherical particle, and you have basically some NX molecules, in the liquid phase. So the liquid phase has just come out, right? So you have this B, which is immersed in a air-rich matrix, and gamma is the diffusion energy. Find the vapor phase of B as a function of its radius of curvature, and that is exactly what I have done here. So you go through this, okay? So you go through this, and you basically will get there is something. So this equation, this is a very famous equation called Oswald-Freundlich equation. Again, this will not be a part of the exam. So the interfacial phenomena, I don't want to go deep into it, but what I want to tell, the crux of it is this. You have this liquid that is condensed in a vapor phase. You have a large vapor phase, and there is a liquid, there is a small droplet of liquid that is condensed. Now the liquid particle contains NX molecules and they form in a vapor. So basically they contain NX molecules and form in a vapor phase which contains initially Ni molecules. Now you have an F. NF is basically Ni minus NX. Now delta G is what? G drop minus G vapor. Okay, and you can now write GV, the small GV, as the free energy per molecule of the vapor, small GL as the free energy per molecule of the liquid drop, and then you have delta G, which is basically, if you look at that, you have NF times GV, GV is per molecule, NX times GL, and then you have 4 pi r square gamma, because R is the radius of the droplet, right? R is the radius of the droplet, 4 pi r square gamma, because gamma is the interfacial energy. So basically you have this, and then what has gone? NIGV, so minus NIGV. Now if I go on expanding, so what I get is NX, which is NF minus NI, GL minus GV plus 4 pi r square gamma. Now VL is the volume occupied per molecule of the liquid, and VV is the volume occupied by per molecule of the vapor. Now you see NX is the number of molecules times VL, which is the volume occupied per molecule of the liquid. Now NX times VL is nothing but 4 third pi r cube. So basically Nx equals to 4/3 pi r cube by 3V. Now that's the liquid droplet, right? And now delta G is nothing but 4 pi r cubed by 3VL GL minus GV plus 4 pi r square gamma, right? That is the surface area. That is the surface energy contribution. Now you have dG, which is VL minus VV times dP, right? V liquid minus V vapor, right? This is volume per, so this is volume per molecule, VL minus VV times dP. This is all per molecule at a constant temperature, right? So VdP minus SdT minus T is not. So basically dG goes minus VVdP. Why? Because VV is much greater than V. So and VB, I can think of this as per molecule, right? So you can use the ideal gas law. So V vapor equals to nothing but kBT by P, where kB is the Boltzmann constant. Right? So you can put kB here. Now what I got is delta G, right? The small delta G. This small delta G basically is telling you minus kBT ln P by P infinity. Now you see there is a change in the Gibbs free energy. Okay, P is now the pressure, right? P is now the vapor pressure between the liquid and the solid, liquid and the vapor. However, originally it was P infinity, right? It has changed from P infinity. So if you look at that, you have delta G is 4/3 pi r cube by VL ln P by P infinity plus 4 pi r square gamma. Now if you want to find out R, the easiest way is to solve for it. How do I solve? I demand that delta G del R equal to 0. So that gives me the critical radius. The droplet. Okay, that gives me the critical radius, the droplet. So then what we basically encounter is the Oswald-Freundlich equation, and where you get this R critical, which is 2 gamma V by E. Right? So there is another very important effect called Gibbs-Thomson effect. Say for example, you have this alpha beta equilibrium, and this is the molar volume of the beta phase, and this is in equilibrium with the alpha phase. Now have a look at this. When initially the yellow curve is G alpha and another yellow curve is G beta, and you alpha and beta share a flat interface with curvature 0 or radius of curvature infinity. However, if the particle, the beta prime, now the beta particle is a sphere or a circle, then what happens? The energy basically, if you look at the common tangent, so you have the blue tangent when you had the original yellow curves. Now your G beta has shifted up, right? It has shifted up. Why is shifted up? Because there is an excess pressure. There is an excess pressure, delta P, which is basically, the excess pressure is nothing but delta P, which is basically 2 gamma by R. Now, with this excess pressure, basically, you have this Vm delta P, basically. So, VdP. So, dG equals to VdP, right? dG equals to VdP. Or delta G equals to V delta P. So, this V delta P, this increase that is given by this orange line here, will lead to another, if you look at this now, the green line, this is your new tangent. Now, if you look at the common tangent, you have seen, so initial equilibrium was here, right? These blue lines, right? This was the one thing. But as soon as I go to this one, I have this guy, and this guy basically come in. So basically what happens, this comes because of, if you look at this is nothing but this chemical potential thing, right? So this is basically mu B alpha equals to mu B beta, or mu B alpha equals to mu beta. Now if you see that condition for your new curvature, basically gives rise to a shift in composition, right? There is a right shift. in composition, by the way, right, of both compositions, the particle as well as the matrix, and this is called Gibbs-Thomson effect. Okay, so I have derived it here, but you can also derive it on your own, and so you can do this. You can basically see that finally you will see that the delta P equal to 2 gamma by R, and you are basically looking at the phase boundaries. Now, if you look at the phase boundaries, there definitely, if the equilibrium has shifted, the phase boundaries are also shifted. That's all I want to tell, and you can actually apply these ideas in multi-component system. I am not talking about Gibbs adsorption and Langmuir adsorption isotherms here. However, if you want to have some separate lecture on it, you please ask me. We can do it. Means I can give you some help there again. I can basically, but again, the interfacial thermodynamics although it is covered, I briefly covered it now and I touched it now. What I am telling is that this is not going to be a part of the final exam. So you don't have to look at it right now, but this is a very, very important topic, and interfacial thermodynamics on its own is like a subject. Now comes the kinetics part. See, the kinetics part here, again, the way I thought is that I introduce the Onseger's postulates. See, there is this driving force, like there is a, so we have already done this. Basically, we looked at, like, if there is a driving force, if there is a chemical potential difference, that chemical potential difference is the driving force, and as a result, there will be mass transfer. Now, if I have mass transfer, at what rate the mass transfer happens is what gives you kinetics. Similarly, if I have a temperature gradient, like T alpha and T beta are not equal, then there is the heat transfer. Heat transfer happens from hot body to cold body in such a way so as to equalize. So this heat transfer, again, basically, again, there is a rate of heat transfer, right? If there is heat transfer, there is a rate of heat transfer. Now, how do I come to these rates? So basically, if you look at Onseger, so Onseger, a famous scientist, okay, who won Nobel Prize for statistical, his contribution to statistical mechanics, basically on physics. So basically, Onseger postulated that the flux is proportional to force. So this capital X here is the force. In fact, let us call this, yeah, this capital X denotes. So I'll tell you. So you have X as force, driving force. And we are telling sum of all forces. So basically, there is a flux which is proportional to the force. Flux, which is, there's a relation between flux and driving force. And flux is what? Flux of species is basically, or flux of any quantity. Say flux of quantity means basically it can be like heat transfer per unit area per unit time. Okay, the amount of energy transfer per unit area per unit time is basically heat flux. Amount of species transfer per unit area per unit time is that for that particular concentration of species transfer per unit area per unit time is the flux. It's a mass. It's a compositional flux, right? Molar flux. You can also have mass flux. So the flux is basically some quantity that is basically passing per unit area per unit time as a response to the driving force. And as a response to the driving force, this flux will happen. And this flux is what is finally going to drive the system towards equilibrium, right? So flux is proportional to driving force. Driving force comes because of some inequality, right? T alpha is not equal to T beta, or mu alpha is not equal to mu beta. So in response, you have this driving force, right? So basically, flux is proportional to force, and Onseger postulated that it is linearly proportional. So you have this Onseger coefficients or this kinetic coefficients which are Lik, some Lik, and some Lik has some properties like it has positive definiteness and all, right? So basically, if I give you an example, so you have, for example, the species concentration. This is the flux. This is compositional flux. Which is proportional to the driving force. Driving force is basically mu is your chemical potential, and grad mu is your driving force. Why? Because U is your potential energy, F equals to minus du dx. Right? So that is exactly what we are looking at. So mu is your chemical potential or energy, and the derivative of energy, the special derivative of energy gives you the driving force. The special driving force, as a result of which there will be flux of this particular species, and the flux is in terms of the compositional flux. So say molar flux, the species I, the species I will have a flux in response to this driving force, so that the equality, again the chemical potential equality is established at equilibrium, right? So basically, another thing that Onseger pointed out is that flux is nothing but velocity, which is the steady state velocity of the particles, times the concentration. Say, for example, if I'm looking at molar flux, that is number of moles of certain species, is basically transferring per unit area per unit time. Now, if I look at, means basically a concentration of species, I am looking at the mass transfer. So if you have this molar flux, then molar flux at steady state, basically it is basically, the molar flux is basically equal to the steady state velocity times composition or concentration. See, concentration is number of moles per unit volume. Now, if you see that number of moles per unit volume, so moles by volume at that velocity is length by time. So this becomes moles, and volume by length is basically so length by volume, right? Volume by length is basically area. Right? So basically that's exactly what we are doing. Now if you have this flux, then there is a drag force. Now if there is a drag force, then basically if there is a drag force, now if you look at this, then there is a work done to overcome this drag force. So if you have F times Vc what times dt. Now if you see, this is force, and you have velocity and you have concentration. So this basically nothing but flux, right? So you have force times flux, and you have this time interval. So basically this basically gives you what? F dot j dt, and this is nothing but delta W, right? This basically, because why? To work on this drag force, what is happening as the flux is happening, there is a work done, and this work done in response to the drag force, and this work done is completely converted to heat. Now, and this converted to heat is an irreversible conversion. There is an entropy production, and if you see, this is the what I am talking about, TdS IRR, which is basically, so del W is nothing but delta Q is nothing but TdS IRR. That is, the IRR is basically for irreversible. So which is basically you have a rate of change of, so basically you have a entropic production rate, right? Rate of entropic production, right? DSIR. The IRR is the irreversible part of the entropy which is getting produced as a result of all these processes, right? Now, if you look at that full V times dt is displacement, you can think of this way. V times dt is nothing but velocity times dt is nothing but displacement, and you have the force, and force times displacement is nothing but. Okay, so basically what we are telling is you have this relation, which is basically called the rate of entropy production, which has to be positive for a process to go on, right? Now again, I don't want to go into the algebra, but I want to tell, say for example, now if I add the continuity equation, now again continuity equation, which is a very important equation of kinetics, is nothing but something or some quantity in, so basically it comes from quantity in minus quantity out. If you remember, initially we looked at open system, so that's what I am trying to do, equals to rate of accumulation or depletion. And remember that you can also have quantity generated within the system, like quantity generated within the system for any time, and you can have like quantity destroyed. So all this gives you a generalized conservation law for the quantity. That quantity can be heat, the quantity can be mass, it can be even momentum, right? And each of these basically give rise to this different type of rate equations. Say, for example, it gives you Navier-Stokes equation, it gives you mass transfer equation or diffusion equation. And if you look at that continuously, so basically if you look at that, you see this is the energy, this is the continuity law for energy, this is the continuity equation for energy. This is nothing but a conservation equation. All continuity equations are conservation equations. Grad dot J is basically divergence of flux, right? The divergence of flux, and and you have this accumulation. So basically the this statement is nothing but del U del T plus this is energy coming in minus energy going out plus energy getting accumulated, right? This part is energy in minus out, this part is energy in minus out, and this part, and this part is the accumulation of energy, and this basically there is a rate of accumulation, and this gives rise to continuity equation. Now if you use this continuity equation, this is also applied for entropy production, right? And this is the entropy flux, right? Now if you think of that, the flux can also be written like Fick's law, right? This is called Fick's first law. J is proportional to grad C, right? Composition of gradient. But in general, as you see from Onsegar, it is flux is proportional to force. Grad C is not driving force. but grad mu is driving force because mu is energy. So according to Onsager, this is a more fundamental relation. So as you look at kinetics, you will see that thermodynamics gives you the driving force, and in response to the driving force there is flux, and the flux and forces are such that the rate of entropy production is always positive. So this is how kinetic laws are in general developed. Okay, so if you have any doubt again here this itself, this kinetics of materials can itself be a full 3 credit course, and we will discuss this later. So but if you have any problem to relate thermodynamics to kinetics, and if you have any problem to relate flux to force, then basically please write to me to my email ID, and I'll be happy to answer your queries. So thank you so much for listening to all the lectures, and if there is any doubt, please do write to me.